Good morning. I am Aditi, studying in BSc Chemistry Honours first year in second semester. Today in this video lecture, we are studying chapter number 6 of electrochemistry. Section A, Electrical Transport, Electrolytic and Metallic Conduction. Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through are known as insulators. Conductors are divided into two classes. First, those which conduct electricity without undergoing any decomposition. These are called electronic conductors. Example, metals, graphite, and certain minerals. As the name indicates, the conduction in this case is due to the flow of electrons. Those which undergoes decomposition when current is passed through their aqueous solution or melt. These are known as electrolytic conductors or electrolytes. Example, solutions of acids, bases, and salts in water fuse salts, etc. In this case, the flow of electricity is due to the movement of ions. Electrolytes are further classified into main categories as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acids, example HCl, HNO3, H2SO4, etc. Strong bases, example NaOH, NKOH, etc. And most of the inorganic salts. These dissociate almost completely in the aqueous solution or in the molten state and hence conduct electricity to a large extent. Weak electrolytes are substances like weak acids, example CH3COOH, HCN, H2CO3, H3PO4, etc. And weak bases, example NH4OH, COOH2, AlOH3, etc. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc., the solutions of which do not conduct electricity are known as non-electrolytes. Factors affecting electrolytic conduction. The conductance of the solution of an electrolyte depends upon the following factors. First, interionic attractions, which depend upon the interactions between the ions of the solute and hence are called solute-solute interactions. On the basis, the substances are classified as strong electrolytes and weak electrolytes as already mentioned. Second, solvation of ions, which depends upon the interactions between the ions of the solute and the molecules of the solvent and hence are called solute-solvent interactions. Third, viscosity of the solvent, which depends upon the solvent-solvent interactions. The effect of all these factors decreases with increase of temperature, hence the electrolytic conduction increases with increase of temperature. On the other hand, the electrical conduction of the electronic conductors decreases with increase of temperature. Alternatively, the factors on which the electrolytic conduction depends are as follows. Nature of the electrolyte. Strong electrolytes ionize almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent and hence conduct electricity also to a small extent. Nature of the solvent. Electrolysis ionize more in a polar solvent, hence greater in the polarity of the solvent. Greater is the ionization and hence greater it is the conduction. Concentration of the solution. Higher the concentration of the solution, less is the conduction. This is because in a weak electrolyte, the ionization is less, whereas in a strong electrolyte, the interionic attractions are high at higher concentrations. With dilution, interionic attractions decreases and hence conduction increases. Temperature. On increases the temperature, the dissociation increases and hence the conduction increases. Difference between metallic conductors and electrolytic conductors. The main points of differences between metallic conductors and electrolytic conductors may be summed up in table 6.1. Metallic conductors. Flow of electricity take place without the decomposition of the substance. Flow of electricity is due to the flow of electrons only, that is, there is no flow of matter. The resistance depends upon the structure and density of the metal and the number of valence electrons per atom. The electrical conduction decreases with increase of temperature. This is because camels start vibrating, which produce hindrance in the flow of electrons. The resistance occurred by metal is also due to vibrating canals. Electrolytic conductors. Flow of electricity takes place accompanied by the decomposition of the substance electrolyte. Flow of electricity is due to the movement of ions and hence there is flow of matter. The electrolytic conduction increases with increase of temperature. This is generally due to increase of dissociation or decrease in the interionic attractions. The resistance shown by an electrolyte solution is due to factors like interionic attractions, viscosity of solvent, etc. 6.2 Electrical resistance and conductance. Every substance offers resistance to the flow of electricity to a small or large extent. The law that gives the exact values of the resistance is known as Ohm's law. It states that if to the ends of a conductor a voltage E is applied and a current I flow through it, then the resistance R of the conductor is EA. Current is generally measured in ampere, whereas voltage is measured in volts. If 1 ampere current flows through a conductor, when a voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm, written as 1 ohm. Thus, according to Ohm's law, in terms of SI base units, and this is explained below, the derivation, it is seen that like metallic conductors, solutions of all electrolytes also obey Ohm's law. It is obvious that a substance which offers greater resistance will allow less electricity to flow through it. This result also flows from Ohm's law, according to which I directly proportional to 1 divided R. The reciprocal of the electrical resistance is called the conductance. It is usually represented by C. Thus, C is equal to 1 divided by resistance. It is a common practice to speak of the conductance of a solution rather than its resistance. The units of conductance are Siemens or reciprocal ohms, written as ohm inverse. For example, if a solution has a resistance of 10 ohms, it is said to have a conductance of 1 by R ohm inverse. Specific, equivalent and molar conductivities. Specific conductivity, or simply called conductivity. It is observed that resistance R of a conductor is directly proportional to the length of the conductor and inversely proportional to its area of cross section. Where P is a constant of proportionally called specific resistance or resistivity, its value depends upon the material of the conductor. The reciprocal of resistivity is known as specific conductivity or simply conductivity. It is denoted by K or K, kappa. Thus is K is the specific conductivity and C is the conductance of the solution. Then specific conductivity of a solution is defined as the conductance of a solution of 1 cm length and having 1 square centimeter as the area of cross section. Alternatively, it may be defined as conductance of 1 cm cube of the solution of the electrolyte, or in terms of SI based units, it is defined as the conductance of 1 meter cube of the conductor. If the volume of the solution is V cm cube, the specific conductivity of such a solution at this dilution V is written as. Similarly, at concentration C, it is represented as equivalent conductivity. For comparing the conductances of the solution of different electrolytes, it is essential that the volumes of the solutions should be same and they must contain such definite amounts of the electrolytes which give ions carrying the same total charge. The best choice is, therefore, to consider the solutions having equal volumes and containing their corresponding gram equivalent weights. The conductance of such a solution is called its equivalent conductivity. Hence, Equivalent conductivity of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cube of the solution when the distance between the electrodes is 1 centimeter and the area of the electrodes is so large that whole of the solution is contained between them. It is represented by lambda. Relationship between equivalent conductivity and specific conductivity. The equivalent conductivity of a solution is usually not found directly but is calculated from the specific conductivity. The relationship between equivalent conductivity and specific conductivity may be obtained as follows. Consider a rectangular vessel with its two opposite walls 1 centimeter apart and made of some metal sheets so that these act as the electrodes. Case number 1. Suppose 1 centimeter cube of the solution containing 1 gram equation of the electrolyte is taken in the vessel. The conductance of this solution will be then its specific conductivity. Further, if 1 centimeter cube of the solution taken contains 1 gram equivalent of the electrolyte, the conductance of the solution will be its equivalent. Conductivity by definition. Thus, when 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is considered, the equivalent conductivity is equal to its specific conductivity. Here the figure 6.2 relationship between equivalent conductivity and specific conductivity. Case number 2. Suppose 4 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken. The conductance of the solution will be still equal to its equivalent conductivity at this dilution, but now there will be 4 cubes each of volume 1 centimeter cube as shown in figure 6.2. The conductance of each 1 centimeter cube of the solution is equal to its specific conductivity so that the total conductance of the solution, that is equivalent conductivity, is 4 times the specific conductivity. In general, if the volume of the solution containing 1 gram equivalent of the electrolyte is V centimeter cube, we have equivalent is equal to specific conductivity into V. In terms of concentration, if the solution has a concentration of C gram equivalent per liter, gram equivalents are present in 1000 centimeter cubes of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 divided by C. Hence the above expression may be written as, you can see this. Note carefully that in the above expression, V is the volume of the solution in centimeter cube containing 1 gram equivalent of the electrolyte and C in the concentration in gram equivalent liter. Molar conductivity. The molar conductivity of a solution is defined in a manner similar to that of the equivalent conductivity as under. The molar conductivity of a solution at a dilution V is the conductance of all the ions produce ions 1 mole of the electrolyte dissolved in V centimeter cube of the solution. When the electrodes are 1 centimeter apart and the area of the electrodes is so large that the whole of the solution is contained between them, it is usually represented by relationship between molar conductivity and specific conductivity. As in the case of equivalent conductivity, the molar conductivity is related to the specific conductivity as follows, where K is the specific conductivity and V is the volume of the solution containing 1 mole of the electrolyte and C is the molar concentration. Units comparing with the equivalent conductivity, the units, you can see this, ohm inverse, centimeter square, mole inverse. Measurement of electrolytic conductance, specific conductivity, equivalent conductivity and molar conductivity. Electrolytic conductance. Conductance is the reciprocal of the resistance, and the conductance can be obtained by the measurement of the resistance, and the latter can be found by the principle of Wheat-Stonebridge method shown in figure 6.3. You can see the figure 6.3, principle of DC, Wheat-Stonebridge method. It consists of 4 arms containing the resistance R1, R2, R3 and R2, R1 is the variable resistance and R2 is the unknown resistance, where null point is obtained, that is, there is no defection in the galvanometer G. Knowing the values of R1, R3 and R2, R2 can be calculated In finding the resistance of the solution of an electrolyte, a special type of cell has to be used such that the solution is present between the two electrodes. The cell thus used is called conductivity cell. It is made up of Pyrex glass and has two platinum electrodes at a fixed distance apart. Shown on right hand side of figure 6.4, you can see the figure 6.4 apparatus for the measurement of the electrolytic conductance. The most serious problem in the measurement of the resistance and hence the conductance of the solution of an electrolyte is that if direct current is used, it causes electrolysis of the solution. As a result, the concentration of the electrolyte near the electrodes changes and this results in the change in the resistance of the solution. These effects are called polarization effects. To overcome this problem, an alternating current in the audio frequency range of 550 to 5000 cycles per second is used. However, when the alternating current is used, ordinary galvanometer fails to detect the null point. Hence, the galvanometer is replaced by earphone. Further, to minimize the polarization effects, the electrodes are coated with platinum black, finally divided platinum deposited on the electrodes electrolytically. To sum up, three modifications required in the usual white stone bridge methods are: source of direct current is replaced by a source of alternating current, which is either an induction coil or a vacuum tube oscillator, which is quieter and gives more symmetrical current. Galvanometer is replaced by an earphone. Electrodes of the cell are coated freshly with platinum black before use. The complete assembly for the measurement of the electrolytic conductance is shown in figure 6.4. A suitable value of the resistance R is introduced from the standard resistance box such that when the sliding contact the jockey J is moved along the stretched wire, the sound in the earphone is reduced to minimum at a point somewhere in the middle of the wire AC, say at the point D. Then if X is the resistance of the electrolytic solution by Wheat-Stonebridge principle. Thus, knowing the resistance R and the balance point D, the resistance X of the electrolytic solution can be calculated. Then specific conductivity or simply called conductivity K is related to the conductance according to the expression. Thus, the specific conductivity of a solution can be determined by measuring its conductance and the distance L between the electrodes and the area of cross section A of each of the electrodes, but it is not convenient to measure L and A accurately. However, for a particular cell, LA is constant and this constant is called cell constant. 1 by A is equal to cell constant. Specific conductivity is equal to conductance into cell constant. Thus, the cell constant of any particular cell can be found by measuring the conductance of a solution whose specific conductivity is known. For this purpose, generally specific conductivities of KCl solutions are used, which are known accurately at different concentrations and temperatures. For a few concentrations at a temperature of 298 Kelvin, these values are given below. Knowing the value of the cell constant, the specific conductivity of the given solution can be determined by measuring its conductance in multiplying the value with the cell constant. Equivalent conductivity is related to the specific conductivity according to the equation. You can see this, where C equation is the concentration of the solution in gram equivalents per liter, the normality of the solution. Thus, knowing the normality of the solution and the specific conductance can be calculated. Fourth, molar conductivity. The molar conductivity is related to the specific conductivity according to the relation, where Cm is the molar concentration. Thus, knowing molar concentration C and the specific conductivity K can be calculated. Conductivity water. For accurate results, the solution should be prepared in a specially purified water whose own conductance is very small. Such water is called conductivity water. Alternatively, to get the resistance of the electrolyte, the resistance of water and used for making the solution may be determined and then subtracted from the resistance of the solution. Here are some numerical problems on specific equivalent and molar conductivities and some formulas and units. You can see this. Variation of conductance, specific conductivity, equivalent conductivity, and molar conductivity with dilution. In general, electrolytic conductance as well as the equivalent conductivity and molar conductivity increase with dilution, whereas the specific conductivity of an electrolytic solution decreases with dilution. The reasons for such a behavior are briefly explained below. The conductance of a solution is due to the presence of ions in the solution. The greater the number of ions, the greater is the conductance as on dilution. More ions are produced in solution, so the conductance should also increase on dilution. The specific conductivity of an electrolyte falls with dilution because the number of current carrying particles, that ions present per centimeter cube of the solution, become less and less on dilution. However, the increase of equivalent and molecular conductivity on dilution is due to the fact that these are the products of specific conductivity and the volume V of the solution containing 1 gram equivalent or 1 mole of the electrolyte. As the decreasing value of specific conductivity is more than the compensated by the increasing volume of V, so that the value of equi and M increase with the dilution. 6.6 Variation of molar conductivity with concentration for strong and weak electrolytes. As already mentioned in the beginning of this section, there are two types of electrolytes, namely strong electrolytes and weak electrolytes. The variation of the molar conductance with concentration or dilution for each of these electrolytes is briefly discussed below. Conductance behavior of strong electrolytes as discussed later in more details in section 6.13. The molar conductivity of strong electrolytes is found to vary with concentration according to the equation, where B is a constant depending upon the type of the electrolyte, the nature of the solvent, and the temperature, and is the molar conductivity and infinite dilution called limiting molar conductivity. This equation is called Debye-Hugel-Onsager equation and is found to hold good at low concentrations. Is plotted against a linear graph is obtained for low concentrations, but it is not linear for higher concentrations as shown in figure 6.5, in which KCl has been taken as an example of strong electrolyte. Further, the curve obtained for a strong electrolyte shows that there is a small increase in a conductance with dilution. This is because a strong electrolyte is completely dissociated in solution, and so the number of the ions remains constant. At higher concentrations, the greater interionic attractions related the motion of ions, and therefore the conductance falls with increases concentrations but decrease in concentration which dilution. The ions are far apart and therefore the interionic interactions decrease, due to which the conductance increases with dilution and approaches a maximum limiting value at infinite dilution, designated as conductance behavior of weak electrolytes. As a weak electrolyte dissociates to a much lesser extent as compared to a strong electrolyte, therefore the conductance of a weak electrolyte is much lower than that of a strong electrolyte at the same concentration. This is shown in figure 6.5, in which acetic acid has been taken as an example of weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very large increase in conductance with dilution, especially near infinite dilution. This is because as the concentration of the weak electrolyte is reduced, more it is ionized. Thus, increase in conductances with increase in concentration is due to the increase in the number of ions in the solution. However, it does not reach a limiting value. Further, from the plots shown in figure 6.5, it is observed that the plot for a strong electrolyte becomes high dilutions and thus can be extrapolated at zero concentration to get the value of the molar conductivity at infinite dilution. However, for a weak electrolyte, such an extrapolation is not possible. It is clear from the plot for acetic acid in figure 6.5. Experimentally also, it is not possible to determine the value for a weak electrolyte as it does not approach a limiting value. The problem was finally solved by Coleridge, who put forward a law known as Coleridge law, as discussed in the next section. Here you can see the figure 6.5. variation of molar conductivity of a strong electrolyte KCl and weak electrolyte CH3COOH with concentration. Here are some problems for practice question examples. Coleridge's law of independent migrations of ions. Coleridge studied the molar conductivity at infinite dilution for a number of pairs of strong electrolytes, each pair having a common cation or anion. Then he calculated the differences of these values for each pair. A few of these results are given in table 6.2. You can see the figure 6.2. It is observed that the difference of what this anion was, similarly the difference values for each pair of salts having the same different anions and a common cation was same. Irrespective of what this cation was, in fact, column 3 in the table 6.2 gives the value for K positive ion minus the values for Na positive ion. Similarly, the last column gives value for Br minus. On the basis of the above observations, Coleridge considered that each ion makes a definite contribution to the total molar conductivity of an electrolyte and infinite dilution. Irrespective of the nature of the electrolyte, this individual contribution of an ion towards the total molar conductivity of the electrolyte is called molar ionic conductivity. As a result of these studies, Coleridge in 1876 put forward a generalization known after him as Coleridge's law. It states as under: the molar conductivity of an electrolyte at infinite dilution is the sum of the limiting ionic conductivities of the cations and the anions, each multiplied with the number of ions present in one formula of electrolyte. Mathematically, you can see this. The above law is the above law is called the law of independent migration of ions because at infinite dilution the dissociation of the electrolyte is complete and there are no interionic effects, so that each ion migrates to the electrode independent of the nature of the other ion with which it is associated. It may be noted that molar conductivity is related to the equivalent conductivity according to the expression, where V plus and V minus are the stoichiometry numbers of the cations and the anions respectively present in the formula. Unit of electrolyte and J plus and J negative are the charges on the cation and the anion respectively. Theories of ionization and Ostwald's dilution law, section B. Arrhenius' theory of ionization or electrolytic dissociation. To explain a number of phenomena related to electrolytes such as conductance, electrolysis, anomalous behavior of electrolytes towards colligative properties, that is higher value of osmotic pressure, elevation in boiling point, dispersion in freezing point and lowering of vapor pressure than expected. Arrhenius in 1887 put forward a theory about the electrolytes. This theory is known as Arrhenius' theory of electrolytes dissociation. The main points of this theory in a modified form are summarized below. An electrolyte, when dissolved in water, splits or dissociates into positively and negatively charged particles called ions. The process is called ionization, or more correctly electrolytic dissociation. You can see the example of NaCl, MgCl2 and Al2SO4 3. The total charge carried by the positive ions is equal to the carried by the negative ions, so that the solution as a whole is electrically neutral. On electrolysis, the positive ions migrates towards cathode and hence are called cations, while the negative ions migrate towards the anode are called anions. The ions formed constantly reunite to form the undissociated molecules. Still, ultimately, there is an equilibrium between the ions and the undissociated molecules. Example of NaCl, MgCl2 and Al2SO4 3. In other words, the whole of the electrolyte may not dissociate into ions. Instead, only a part of the electrolyte may dissociate into ions. The fraction of the total number of molecules of the electrolyte that dissociates into ions is called the degree of ionization or dissociation. It is usually denoted by degree of dissociation is equal to number of molecules dissociated divided by total number of molecules taken. The degree of dissociation increases with dilution and becomes maximum at the infinite dilution. The conductance of the electrolytic solution is due to the ions produced by the dissociation of the electrolyte. Greater the dissociation, the higher is the conductance. Substances like minerals, alkalis, and most of the salts which show a high conductance is due to the fact that they possess high degree of dissociation. Their molecules are almost completely dissociated into ions in the aqueous solutions. Such substances are called strong electrolytes. On the other hand, substances like organic acids and bases and some of the inorganic acids like H2CO3, H3PO4, etc., and inorganic bases like NH4OH, CaOH2, etc., which show poor conductances due to the fact that they possess low degree of dissociation. They are only partly dissociated in the aqueous solutions. Such substances are called weak electrolytes. The ions produced by the dissociation of an electrolyte below like molecules towards colligative properties. For example, each NaCl molecules dissociates to give ions with Na positive and Cl negative. Hence, the observed value of any colligative property is double than the expected value. The properties of an electrolyte are the properties of its ions. For example, the properties of an acid are due to the H positive ions furnished by it in the aqueous solution. Similarly, the properties of a base are due to the OH negative ions produced in the aqueous solution. Factors on which the degree of dissociation depends. The degree of dissociation of an electrolyte in the solution depends upon the following factors. Nature of the solute. In aqueous solution, some electrolytes like acids, alkalis, and most of the salts are almost completely ionized. These are called strong electrolytes. On the other hand, some electrolytes like organic acids and bases and some inorganic acids and bases ionize only to a small extent. These are called weak electrolytes. Nature of the solvent. Every solvent has some definite value of the electrolytic constant, which is defined as its power to weaken or cut off the forces of attraction present between the ions of the electrolyte. Figure 6.6, you can see the figure 6.6. Water has the highest dielectric constant is equal to 80 compared with vacuum taken as unity. Thus, the dissociation of an electrolyte is maximum in water as compared to that in the other solvents. Concentration. Degree of dissociation an electrolyte increases with dilution and becomes maximum at infinite dilution, that is zero concentration. Presence of common ions. The degree of dissociation of an electrolyte decreases when another electrolyte is present which furnishes a common ion. This effect is small common ion effect. For example, dissociation of NH4OH decreases in the presence of NH4Cl. Temperature. As the temperature is increased, more of the molecules split into ions, degree of dissociation increases. Evidence in favor of Arrhenius theory. The direct evidence for the Arrhenius theory came from the X-ray studies which showed that solid substances which behaved as strong electrolytes existed in the ionic form and not in the molecular form. Example, NaCl is found to exist as Na positive Cl negative. Further, Arrhenius theory is able to explain a number of facts and phenomena related to electrolytes which lend support to the theory. A few of these phenomena are briefly explained below. Electrolytic conductance. It has been explained in postulate 6 of the Arrhenius theory that all the conductance of the solution of an electrolyte is due to the presence of the ions produced by the electrolyte dissociation. Strong electrolyte possesses high degree of dissociation and hence show greater conductance, whereas weak electrolytes dissociate to a small extent and hence show low conductance. Variation of conductance with dilution. It is observed that the specific conductance decreases whereas conductance as well as equivalent conductance increases with dilution. The explanation is evidently based on postulates 5 and 6 of the Arrhenius theory. The equivalent conductance and the dissociation of the electrolyte vary in such a similar manner with dilution that the degree of dissociation of an electrolyte at any concentration can be expressed in terms of equivalent or molar conductances as follows. Where is the equivalent conductance at given concentration is the equivalent conductance at infinite dilution or molar conductances at concentration C and at infinite dilution respectively. Electrolysis. According to postulate 1 of the Arrhenius theory, an electrolyte when dissolved in water dissociates into ions. Thus the function of the electricity is only to direct the ions toward the electrodes. Colligative properties. The reason for the anomalous results observed about the colligative properties for the solution of electrolytes has already been given in postulate 6 of the Arrhenius theory. The quantitative explanation of anomalous results about colligative properties of strong electrolytes was given by Ventov. He introduced a factor I called Ventov factor, defined by the expression I is equal to observed value of the colligative property divided by normal value of the colligative property. This factor I could be determined experimentally by dividing the observed value of colligative property, osmotic pressure, lowering of vapor pressure, elevation in boiling point, or depression in freezing point, with that of the solution of a normal substance like sucrose having the same molar concentration. The Ventov factor I could be used to find the degree of dissociation as follows. For electrolytes of the type AB, example NaCl, KCl, etc., suppose we start with 1 mole of the electrolyte and is the degree of dissociation. Then we have number of moles before dissociation, number of moles after dissociation, total number of moles after dissociation. Assuming normal behavior, if there were no dissociation, number of moles would have been 1. Since the value of a colligative property is proportional to the number of particles, which is turned in directly proportional to the number of moles, Ventov factor I would be given by. For electrolytes of the type AB2, starting with 1 mole of the electrolyte and assuming that alpha is the degree of dissociation, the values of alpha found that these measurements and those found from the expression were found to be in fair agreement with each other for a number of electrolytes. This lent a great support to the Arrhenius theory. In general, for an electrolyte of the type AXBY, and we have fifth, ionic nature of reactions. As stated in postulate 7 of the Arrhenius theory, the properties of an electrolyte are the properties of its ions. Thus, the reaction between NaCl solution and AgNO3 solution forming a precipitate of AgCl may be explained as follows. NaCl in aqueous solution ionizes as AgNO3 also ionizes in the aqueous solution as. When the above two solutions are mixed, we have the reaction between any two ionic compounds in aqueous solution take place in a similar manner. Heat of neutralization. The heat of neutralization is defined as the amount of heat evolved when 1 gram equivalent of the acid is neutralized by the base or 1 gram equivalent of the base is neutralized by the acid. The heat of neutralization of a strong acid with a strong base is always the same. Thus is explained by the Arrhenius theory as follows. Suppose the strong acid is HCl and the strong base is NaOH, as both are completely dissociated in the aqueous solution. The reaction between them may be written as cancelling out the common ions on both sides, the above reaction reduces to. Thus, neutralization may be defined simply as the process in which S positive ions given by the acid combine with the OH negative ions given by the base to form unionized water molecules. As 1 gram equivalent of any strong acids in aqueous solution gives the same number of H positive ions, and 1 gram equivalent of any strong bases gives the same number of OH negative ions. The neutralization involves the combination between the same number of H positive ions and OH negative ions. Hence, the heat of neutralization of a strong acid with a strong base is always the same. If either the acid or the base or both are weak, the heat of neutralization is less than 13.7 kcal. The reason for the lower value is that of a weak acid or a weak base dissociates to a small extent and some heat is used up to bring out about its dissociation. For example, if the weak acid is acetic acid and the base is NaOH, they dissociate in the aqueous solution as follows. As H positive ions are removed by combination with OH negative ions, the equilibrium shifts towards right. More of acetic acid dissociates for acetic acid, the heat of dissociation. Hence, the net heat involved. Similarly, the heat of dissociation of NH4OH, so that the heat of neutralization of NH4OH with KCl is 13.7 minus 1.4 is equal to 12.3 kg. Salt hydrolysis. It is defined as the process in which the salt reacts with water to give back the acid and base. Salt plus water give back the acid plus base. Depending upon the relative strengths of the acid and the base produced, the resulting solution is acidic, basic or neutral. These observations are also explained on the basis of Arrhenius theory. Ostwald's dilution law. According to Arrhenius' theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ions and the undissociated molecules. For example, for a binary electrolyte AB, we have Ostwald in 1888 pointed out that the law of chemical equilibrium can be applied to the ionic equilibrium. As a result, he obtained an important relationship known as Ostwald's dilution law. Suppose the initial concentration of the binary electrolyte AB in the solution is C moles liter and alpha is the degree of dissociation, then we will have. Applying the law of chemical equilibrium, we get the equilibrium constant K for the equilibrium AB A plus B negative is called the dissociation constant or ionization constant of the electrolyte AB and may be represented by Kd or K1 Ki. Like any other equilibrium constant, Kd is constant only at constant temperature. The units of Kd will be the same as those of the concentration C. If the degree of dissociation alpha is very small, as is usually the case for a weak electrolytes, at ordinary concentrations alpha can be neglected in comparison to 1 in the denominator of expression. Then the approximate formulas becomes, you can see this. Equations 1 and 2 are the two expressions of Ostwald's dilution law. Expression 2 can be expressed in words as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is inversely proportional to the square root of the initial molar concentration. Further, as C is the concentration in moles liter, therefore the volume V of the solution containing 1 mole of the electrolyte will be 1 C liters. Puring 1 divided by C is equal to V. The expressions 1 and 2 can also be written as you can see this, where V is the volume of the solution in liters containing 1 mole of the solute. The Ostwald's dilution law may also be defined as follows. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is directly proportional to the square root of the volume in liters containing 1 mole of the electrolyte. Validity of Ostwald's dilution law. To test the validity of Ostwald's dilution law, to verify the law experimentally, the degree of dissociation alpha was determined from conductance measurements using the formula. At different concentrations for a number of electrolytes, for such electrolyte, the data were fitted in equation 1 to see whether the value of Kd comes out to be constant or not. It was observed that the value of Kd comes out to constant only for weak electrolytes, and that too when the concentration of the solution is not too high for dilute solutions. The value of Kd does not come out to be constant for strong electrolytes. Thus, it may be conducted that Ostwald's dilution law is valid only for weak electrolytes in dilute solution. That is why it is called dilution law. And it does not hold good for strong electrolytes. As an example, the results of weak electrolytes, namely CH3COOH, and those of a strong electrolyte, namely KCl, are given in table 6.2 below. Dissociation constants of CH3COOH and KCl at different concentrations using Ostwald's dilution law. Importance of Ostwald's dilution law. Ostwald's dilution law is applicable to weak electrolytes. Only as such it is very useful in the calculation of the dissociation constants Kd of the weak acids and weak bases by determining the degree of dissociation from conductance measurements at any concentration C. Having determined the value of Kd, which is constant for a particular weak acid or weak base at a particular temperature, the degree of dissociation of the weak acid or weak base can be calculated at any concentration. Here, the numerical problems on Ostwald's dilution law. Here some problem practice questions. Limitations of Arrhenius theory. No doubt Arrhenius theory was able to explain a number of facts and phenomena, but soon a number of objections were raised against this theory, especially when applied to strong electrolytes. A few of these objections are as follows. Arrhenius suggested that ionization of the electrolyte takes place when dissolved in water. However, X-ray studies have shown that many such electrolytes are already in the ionized state. Hence, the word ionization has been replaced by the word dissociation. As an electrolyte can conduct electricity even in the molten state, it shows that the dissociation of the electrolyte takes place even in the molten state. As such, the function of water could not be explained by Arrhenius theory. In other words, it could not explain why the dissociation takes place at all. The most serious objection against the Arrhenius theory was its utter failure when applied to strong electrolytes. Oswald dilution law, which is derived on the basis of Arrhenius theory using the concept of ionic equilibrium, fails for the strong electrolytes. Constant value of the dissociation constant K is not obtained. The degree of dissociation of strong electrolytes calculated from conductance measurement was found to be different from the calculated from colligative properties. The values were found to be nearly same only for univalent electrolytes. Strong electrolytes are almost completely dissociated even at moderate concentration, 100% at all concentration. Hence, Arrhenius' view that conductance increases with dilution because the dissociation increases does not make any sense in case of strong electrolytes. The increase in conductance with dilution must be therefore due to some other factors called interionic effect discussed in the next section. The ratio is therefore better called apparent degree of dissociation or conductance ratio only. The failure of Ostwald's dilution law for the strong electrolytes is evidently because of two reasons. Firstly, strong electrolytes are almost completely dissociated in the solution, therefore, the question of equilibrium does not rise. Secondly, the calculation of alpha from is faculty as mentioned above. Explanations of the anomalous behavior of strong electrolytes, interionic effects, Debye-Huckel theory. The increase of equivalent conductance but dilution in case of weak electrolytes can be easily explained on the basis of Arrhenius theory, which suggests that the conductance increases because the dissociation of the weak electrolyte increases with dilution. However, in case of strong electrolytes, as they are almost completely dissociated, even at moderate concentration, the increase in equivalent conductance with dilution must be due to some other factors. The qualitative explanation put forward it as follows. The conductance of the solution of an electrolyte depends not only upon the number of ions but also upon their speed. In case of weak electrolytes, the increase in conductance with dilution is due to the increase in the dissociation of the electrolyte. Due to increase in the number of ions, the speeds of the ions in their case are not much affected by change in concentration because the number of ions produced is so small that the distance between them is quite large, so that there is no interference in the movement of an ion by the other ions. However, in case of strong electrolytes, the number of ions produced on dissociation is so large that the freedom of movement of an ion is hindered by the other ion present around it when the solution is diluted. The ionic interference decreases and hence ionic speed increases, and so does the equivalent conductance. The first successful attempt to explain the variation of equivalent conductance of strong electrolytes but dilution or concentration quantitatively was made by Debye and Huckel 1923. The fundamental idea underlying their work is that because of electrical retractions among the oppositively charged ions, each ion is surrounded by a large number of oppositively charged ions, which may be regarded as an ionic atmosphere of opposite charge, and this affects the speed of the ion is an electric field. The electrical attractions among the oppositively charged ions, which affect the speed of an ion in the electric field, are called interionic effects. There are two such effects which are briefly described below: relaxation effect or asymmetric effect. In the solution, each ion is surrounded by an ionic atmosphere of opposite charge. So long as no electric field is applied, the ionic atmosphere remains symmetrical around the central ion. However, when a current is passed through the solution, the central ion moves towards the oppositively charged electrode. As it is moving out of the ionic atmosphere, it has to rebuild an ionic atmosphere of opposite charge around it, and the old ionic atmosphere dies out. However, neither the destruction of the old ionic atmosphere nor the formation of the new ionic atmosphere takes place instantaneously. Each of them takes some time called the time of relaxation. During this time, the old ionic atmosphere pulls the moving ion backward and hence retard in motion. Hence, this effect is called relaxation effect. Alternatively, it may be argued that as the central ion moves, the symmetry of the ion's atmosphere is lost. More ions of the ionic atmosphere are left behind than are present on the front. The excess ions of the ionic atmosphere present behind the moving ion drag the ion backward and retard its motion. Thus, the effect arises because of the asymmetry of the ionic atmosphere of the moving ion, and hence is also called asymmetric effect. Electrophoretic effect. When EMF is applied, the central ion moves in one direction and the oppositively charged ionic atmosphere moves in the opposite direction. As this ionic atmosphere moves, the solvent molecules associated with it follows move along with it. Thus, the flow of the ionic atmosphere and that of the solvent molecules attached to it takes place in a direction opposite to that of the movement of the central ion. In other words, the central ion is moving against the stream, hence its motion is retarded. This effect is called electrophoretic effect, since it is similar to that opposite the movement of colloidal particles in an electric field. Besides the above two effects, the third retarding force is the normal frictional resistance offered by the medium, which depends on the viscosity of the medium, its dielectric constant, etc. You can see the figure 6.8, movement of a central ion in a direction opposite to that of the ionic atmosphere and the associated solvent molecules. Based upon the above ideas, Debye and Huckel 1923 derived a mathematical expression for the variation of equivalent conductance with concentration. This equation was further improved by Ohm-Sager 1926 to 27, and now the equation is known as Debye-Huckel-Ohm-Sager equation, or simply Ohm-Sager equation. For a univalent electrolyte, it is written in the form as D and N are constant for particular solvent. Therefore, at constant temperature, the above equation can be written in the form. You can see the equation number 2, where A and B are the constants for a particular solvent at a particular temperature. Verification of the Ohm-Sager equation. Two tests can be readily performed to verify the Ohm-Sager equation. These are the plot of versus should be linear. The slope of the line should be equal to A plus B, calculated by substituting the values of various constants directly. You can see the figure 6.9 tests of Ohm-Sager equation. The line represents theoretical slopes, whereas small circles represents the experimentally observed points. Thus, the agreement is very fair. In case of certain salts like NaCl, KCl, it is observed that the agreement is excellent at low concentrations, but at appreciable concentration, the measured conductances are somewhat higher than those calculated from Ohm-Sager equation. It is probably because there may be some other retarding forces which have been neglected. Thus, the anomaly of the strong electrolytes is not yet fully resolved. From equation 2, it may be seen that at infinite dilution. Significance of Debye-Huckel theory. The significance of Debye-Huckel theory obviously lies in the fact that it is able to explain why the equivalent conductance of a strong electrolyte at any concentration is less the limiting value of at infinite dilution in spite of the complete ionization of the strong electrolyte. You can see the section C, migration of the ions and transport numbers. Migration of ions. When electricity is passed through the solution of electrolyte, the ions present in solution are liberated at the electrodes. Electrolysis occurs. This movement of ions towards the oppositively charged electrodes is called migration of ions. That ions actually exit independently and move with the passage of current in solution towards the oppositively charged electrodes can be seen experimentally as follows. Take a U-tube, fill its lower portion of CuCr2O7 jelly obtained by mixing a 5% solution of agar-agar and a mixture of CuSO4 and K2Cr2O7 and allow it is to set. The jelly is given. Demonstration of the migration of ions. You can see the figure 6.10. In color, to mark the position of jelly, some charcoal is scattered over the green jelly. Over charcoal in both the limbs is added KNO3 solution in agar-agar, KNO3 jelly, and then aqueous solution of KNO3, figure 6.10. When current is passed, blue colored Cu2 positive ions are seen moving towards negative electrode and yellow colored Cr2O2 7 ions are seen moving towards positive electrode. After some time, the two types of ions are seen moving with well-defined boundaries. The experiment clearly shows the migration of ions, migration velocity of ions, and change in concentration heteros the theoretical device. The dilution must be therefore due to some other factors called interionic effect discussed in the next section. The ratio is therefore better called apparent degree of dissociation or conductance ratio only. The failure of Ostwald's dilution law for the strong electrolytes is evidently because of two reasons. Firstly, strong electrolytes are almost completely dissociated in the solution. Therefore, the question of equilibrium does not rise. Secondly, the calculation of alpha from is faculty as mentioned above. Explanations of the anomalous behavior of strong electrolytes, interionic effects, Debye-Huckel theory. The increase of equivalent conductance but dilution in case of weak electrolytes can be easily explained on the basis of Arrhenius theory, which suggests that the conductance increases because the dissociation of the weak electrolyte increases with dilution. However, in case of strong electrolytes, as they are almost completely dissociated, even at moderate concentration, the increase in equivalent conductance with dilution must be due to some other factors. The qualitative explanation put forward it as follows. The conductance of the solution of an electrolyte depends not only upon the number of ions but also upon their speed. In case of weak electrolytes, the increase in conductance with dilution is due to the increase in the dissociation of the electrolyte. Due to increase in the number of ions, the speeds of the ions in their case are not much affected by change in concentration because the number of ions produced is so small that the distance between them is quite large, so that there is no interference in the movement of an ion by the other ions. However, in case of strong electrolytes, the number of ions produced on dissociation is so large that the freedom of movement of an ion is hindered by the other ion present around it when the solution is diluted. The ionic interference decreases and hence ionic speed increases, and so does the equivalent conductance. The first successful attempt to explain the variation of equivalent conductance of strong electrolytes but dilution or concentration quantitatively was made by Debye and Huckel 1923. The fundamental idea underlying their work is that because of electrical retractions among the oppositively charged ions, each ion is surrounded by a large number of oppositively charged ions, which may be regarded as an ionic atmosphere of opposite charge, and this affects the speed of the ion in electric field. The electrical attractions among the oppositively charged ions, which affect the speed of an ion in the electric field, are called interionic effects. There are two such effects which are briefly described below: relaxation effect or asymmetric effect. In the solution, each ion is surrounded by an ionic atmosphere of opposite charge. So long as no electric field is applied, the ionic atmosphere remains symmetrical around the central ion. However, when a current is passed through the solution, the central ion moves towards the oppositively charged electrode. As it is moving out of the ionic atmosphere, it has to rebuild an ionic atmosphere of opposite charge around it, and the old ionic atmosphere dies out. However, neither the destruction of the old ionic atmosphere nor the formation of the new ionic atmosphere takes place instantaneously. Each of them takes some time called the time of relaxation. During this time, the old ionic atmosphere pulls the moving ion backward and hence retard in motion. Hence, this effect is called relaxation effect. Alternatively, it may be argued that as the central ion moves, the symmetry of the ion's atmosphere is lost. More ions of the ionic atmosphere are left behind than are present on the front. The excess ions of the ionic atmosphere present behind the moving ion drag the ion backward and retard its motion. Thus, the effect arises because of the asymmetry of the ionic atmosphere of the moving ion, and hence is also called asymmetric effect. Electrophoretic effect. When EMF is applied, the central ion moves in one direction and the oppositively charged ionic atmosphere moves in the opposite direction. As this ionic atmosphere moves, the solvent molecules associated with it move along with it. Thus, the flow of the ionic atmosphere and that of the solvent molecules attached to it takes place in a direction opposite to that of the movement of the central ion. In other words, the central ion is moving against the stream, hence its motion is retarded. This effect is called electrophoretic effect, since it is similar to that opposite the movement of colloidal particles in an electric field. Besides the above two effects, the third retarding force is the normal frictional resistance offered by the medium, which depends on the viscosity of the medium, its dielectric constant, etc. You can see the figure 6.8, movement of a central ion in a direction opposite to that of the ionic atmosphere and the associated solvent molecules. Based upon the above ideas, Debye and Huckel 1923 derived a mathematical expression for the variation of equivalent conductance with concentration. This equation was further improved by Ohm Sagar 1926 to 27, and now the equation is known as Debye-Huckel-Owen-Sager equation, or simply Owen-Sager equation. For a univalent electrolyte, it is written in the form as G and N are constant for particular solvent. Therefore, at constant temperature, the above equation can be written in the form. You can see the equation number 2, where A and B are the constants for a particular solvent at a particular temperature. Verification of the Owen-Sager equation. Two tests can be readily performed to verify the Owen-Sager equation. These are the plot of versus should be linear. The slope of the line should be equal to A plus B, calculated by substituting the values of various constants directly. You can see the figure 6.9 tests of Owen-Sager equation. The line represents theoretical slopes, whereas small circles represents the experimentally observed points. Thus, the agreement is very fair. In case of certain salts like NaCl, KCl, it is observed that the agreement is excellent at low concentrations, but at appreciable concentration, the measured conductances are somewhat higher than those calculated from Owen-Sager equation. It is probably because there may be some other retarding forces which have been neglected. Thus, the anomaly of the strong electrolytes is not yet fully resolved. From equation 2, it may be seen at infinite dilution. Significance of Debye-Huckel theory. The significance of Debye-Huckel theory obviously lies in the fact that it is able to explain why the equivalent conductance of a strong electrolyte at any concentration is less the limiting value of at infinite dilution in spite of the complete ionization of the strong electrolyte. You can see the section C, migration of the ions and transport numbers. Migration of ions. When electricity is passed through the solution of electrolyte, the ions present in solution are liberated at the electrodes. Electrolysis occurs. This movement of ions towards the oppositively charged electrodes is called migration of ions. That ions actually exit independently and move with the passage of current in solution towards the oppositively charged electrodes can be seen experimentally as follows. Take a U tube, fill its lower portion of CuCr2O7 jelly obtained by mixing a 5% solution of agar-agar and a mixture of CuSO4 and K2Cr2O7 and allow it is to set. The jelly is given. Demonstration of the migration of ions. You can see the figure 6.10. In color, to mark the position of jelly, some charcoal is scattered over the green jelly. Over charcoal in both the limbs is added KNO3 solution in agar-agar, KNO3 jelly, and then aqueous solution of KNO3, figure 6.10. When current is passed, blue colored Cu2 positive ions are seen moving towards negative electrode and yellow colored Cr2O27 ions are seen moving towards positive electrode. After some time, the two types of ions are seen moving with well-defined boundaries. The experiment clearly shows the migration of ions, migration velocity of ions, and change in concentration plus Hitrov's theoretical device. According to Faraday's second law of electrolysis, when the same quantity of electricity is passed through solutions of different electrolytes, the ions are always liberated in equivalent amounts. This, however, does not necessarily mean that the ions move with the same speed. It may be illustrated as follows. Consider a cell containing the solution and provided with the anode A and the cathode C. You can see the figure 6.11, migration velocity of ions and change in concentration when electrodes are not attacked. Let the solution lying between the electrodes A and C be divided into three compartments: the anodic, the middle, and the cathodic. With the help of the imaginary porous partitions A and B shown by dotted lines before electrolysis, suppose there are 13 pairs of ions, plus sign indicating the cation and the negative sign the anion, 4 being present in each of the anodic and the cathodic compartments and 5 in the middle as shown in the position I. Now the following different cases may be considered. Case number 1. When only anions, negative move, let two anions have cathodic compartment and either anodic compartment. We get the position if although the cations have not moved, still we see that the number of ions liberated in the same or both the electrodes, but we see the concentration in anodic chamber has not alterated while the in cathodic chamber has fallen by 2 molecules. Similarly, we can show that if cations are capable of movement and two of them enter cathodic compartment from anodic compartment, then there will be a fall in concentration of two molecules in the anodic chamber. Thus, we see that the velocity of an ion is proportional to the fall of concentration of chamber from where it leaves. Case 2. When cations and anions move at the same rate. Let us Let us assume that two cations move from anodic compartment to the cathodic compartment and two anions move from the cathodic compartment to the anodic compartment. Then we get position third. In this case, there is fall in concentration of two molecules in each compartment, but we find that the number of ions liberated at both the electrodes in the same. Fall in concentration in the anodic compartment due to migration of Ag positive ions, gram equivalents. Further from figure 6.12, it may be seen that fall in concentration around cathode is equal to increase in concentration around anode is equal to y gram equivalents. Thus, the speed ratio in this case will be given by speed of Ag positive ions divided by speed of NO3 negative ion is equal to x minus y divided by y. Transport number. As seen in section 6.14, when an electric current is passed, the ions migrate towards the electrodes. Thus, the electric current is carried by ions. Each ion carries a definite fraction of the total current depending upon its speed. The fraction of the total current carried by an ion is called its transport number or transference number or Hitrov's number. Greater the speed of the ion, greater the amount of the current it will carry with it, and hence greater will be its transport number. Let UA and UC be the speeds of the anion and the cation respectively, since current is carried only by ions. Total current carried is equal to current carried by an ion plus current carried by cation. Transport number of anion, similarly transport number of cation will be, you can see and there are two important relations, you can see this. That is, sum of transport numbers of an ion and cation of an electrolyte is always unity. Thus, no current is lost in any other function and the whole of the current is carried by the ions. Determination of transport numbers. There are a number of methods for determination of transport number. Number 1, Hitrov's method, Lode's moving boundary method, and EMF method. Out of these, the two first methods are described below. Hitrov's method. The method is based upon the principle that the fall in concentration around an electrode is proportional to the speed of the ion moving away from it. You can see this. Referring to figure 6.11, it may be seen that the number of gram equivalents lost from both the compartments is equal to the number of gram equivalents discharged on each electrode. This in turn can be found by placing a silver or a copper voltmeter in series as according to Faraday's second law. When the same quantity of electricity flows through the silver or copper voltmeter, the same number of gram equivalents of Ag or Cu will be deposited. Thus, the above formula reduces to. Thus, the determination of the transport number of the cation involves the determination of the number of gram equivalents lost from the anodic compartment and the number of gram equivalents of Ag or Cu deposited in the voltmeter placed in series with the apparatus. However, it is important to note that the above result is applicable only when the electrodes are not attacked by the ions. If the electrodes are attacked, the result is calculated in a different manner as discussed in the calculation at the end of this section. To determine the transport number of the cation, there is no need to find the loss in the concentration of the cathodic compartment because NC can be calculated directly from the equation. Apparatus. Evidently, the apparatus should be such that it should consist of three components, namely the anodic, the cathodic, and the central compartments. The solution of these three compartments should not mix with each other on electrolysis, and it should be possible to take out the solution of any compartment without disturbing the solutions of other compartments. The above requirements are met in the apparatus shown in figure 6.13. It consists of U-tube joined on its two sides to two vertical bubbled glass tubes. All the three, the U-tube and the two vertical tubes, have got the stop cocks at their bottom. The U-tube is also provided with two stop cocks, one on either side at the top, so as to cut off the various compartments from each other when required. In the two vertical tubes are placed the anode and the cathode separately. These are of platinum, especially the anode, if it desired that these should not be attacked by the ions. Alternatively, the anode and the cathode of silver or copper are taken depending upon whether transport number of Ag positive ions or Cu positive ions to be determined. in which case the anode is attacked by the ions. The apparatus is connected to a silver or copper voltmeter, also called colmeter, is series with the apparatus together with a battery, a rheostat, a key, and a milliammeter as shown in given 6.13 figure. Hitrop's transport number apparatus for the determination of transport number. You can see the figure 6.13. Here the procedure. The apparatus is filled with the solution of the electrolyte, the transport number of whose ions is to be determined. A silver or copper voltmeter is placed in series with the apparatus and the various connections made as shown in figure 6.13. Before electrolysis, the concentration of the electrolyte is found by titrating a known weight of the solution against a suitable reagent, against KSCN solution for AgNO3 solution, and against hypo solution for CuSO4 solution after adding Ki into it. Now a current of 0.01 to 0.02 ampere is passed for 2-3 holes. A low current is used so that the change in concentration around the electrodes is not too high as the otherwise the diffusion may take place. After electrolysis, the solution from the anodic compartment is taken out, weighed, and then titrated as before to know the amount of the electrolyte present. The weight of the silver deposited in the silver voltmeter or that of copper in case copper voltmeter is used is also determined. The solution from the central compartment is also taken out and titrated to see that there is no change in concentration within the experimental errors. In case a change in concentration is observed, the experiment is repeated. It is important to note that in these measurements, the weights of the solution are taken instead of volumes. This is necessary because after electrolysis, the density of the solution changes and so does the volume. Calculations. The method of calculation may be illustrated by taking the example of AgNO3 as the electrolyte and using silver voltmeter in series. Case 1. When the electrodes are not attacked, when platinum electrodes are used. After electrolysis, suppose weight of the anodic solution taken out, weight 1g, and you can see the complete case 1. Case 2. When the electrodes are attacked, when silver electrodes are used, in this case as the NO3 negative ions reaching the anode attack the silver anode, there is increase in the concentration of Ag positive ions in the anodic solution. In this case we will have increase in the concentration of the anodic solution. The increase in the concentration takes place in spite of migration of Ag positive ions from the anodic compartment to the cathodic compartment. If no Ag ions had migrated from the anodic compartment, the increase in the concentration of Ag ions in the anodic compartment would have been higher and equal to ZZ equation of Ag. Here the numerical practice questions. 2. Moving boundary method. This method is based upon the fact that the transport number of the cation and the anion are given by. Thus, by determining the speeds of the cation and the anion, the transport number can be calculated. The apparatus used in shown in figure 6.14. You can see the figure 6.14 moving boundary method for determination of transport number. It consists of a long tube mounted vertically and fitted with the platinum electrodes on two sides as shown in figure 6.14. The salt Ba under investigation is made into solution and then placed between the solution of two other salts Ba and Ba, one having as common cation and the other having common anion. The three solutions are arranged in an order of increasing density downwards to avoid mixing effects. The original boundaries are A and B even if the solutions are colorless. The boundaries can be observed because of the differences in the refractive indices of the solution in order that the boundaries may remain sharp throughout the experiment. Factors on which transport number depends. It has been stated earlier that the transport number of an ion is directly proportional to the speed of the ion, which in turn depends upon a number of factors. Nature of the ion. Normally, the smaller the size of the ion, greater is its speed and hence higher it is transport number. For example, the transport number of H positive ion in 0.1 HCl is greater than that of Na positive ion in 0.1 NaCl or K positive ion in 0.1 NKCl, etc. Nature of the other ion present. For example, the transport number of Cl ion in HCl is different from the HCl ion in HCl. This maybe is explained below. Third, hydration of the ions. The speed of an ion and hence its transport number is very much affected by the hydration of the ions. For example, Li ions are smaller in size than Na ions and hence may be expected to have higher transport number than Na ions, but the actual position is otherwise. This is because Li ions are more hydrated than Na ions. Similarly, Na ions have a smaller transport number than K ions. Concentration. The number of an ion changes with concentration, but the change is very small. However, in case the increase in concentration results into the formation of a complex ion, the transport number changes significantly. Temperature. As the temperature increase, the ions and to approach a transport number value of 0.5 at this temperature, equal fraction of the current is carried by the cation and the anion. In case of ions having transport number less than 0.5 at ordinary temperature, the transport number increases with increase of temperature. In case of ions having transport number greater than 0.5 at ordinary temperature, the transport number decreases with increase of temperature. When the transport number of the ions are approximately 0.5 as in KCl, the effect of temperature is very small. Here the figure 6.15 electrolysis of concentrated CdI2 solution. Interionic effects. How the speed of the ion is affected by the interionic effects have been discussed in section 6.13 under Debye-Huckel theory. Here the section D, applications of conductance measurements. Introduction. Let us first recapitulate a few terms, relations and concepts related to conductance. Conductance, it is reciprocal of resistance, units, moles or Siemens, specific, equivalent and molar conductivities. The conductivities of 1 cm cube of the solution is called specific conductance. The conductance of a solution containing 1 gram equivalent of the electrolyte is dissolved in VCC of the solution is called its equivalent conductance. Relation between equivalent conductance and specific conductance, you can see this. Here the relationship between molar conductance and specific conductance, you can see this. Colerage's law. It states as follows: the equivalent conductance of any electrolyte at infinite dilution is the sum of the two values, one depending upon the cation and the other upon the anion mathematically. In terms of molar conductivity for an electrolyte, you can see this. It is interesting to point out that through all electrolytes are completely dissociated at infinite dilution, yet their molar conductances at infinite dilution are very widely. This is explained on the basis of large differences in the speeds of their ions. For example, molar conductance of HCl at infinite dilution is much larger than that of NaCl. Chloride being a common ion, the difference is evidently due to larger speed of H positive ions than Na positive ions. Ionic mobility. As the speed of the ion also depends upon the potential difference applied, hence a term ionic mobility has been introduced, which is defined as follows. The ionic mobility is the distance travelled by an ion in centimeter second under a potential gradient of 1 volt per second. Relationship between ionic conductance and ionic mobility. As explained above, the term ionic conductance differs from the term ionic mobility. The two are found to be related according to the equation, in which the ionic mobility and the ionic conductance are the limiting values, that is, when the solution are very dilute so that the electrolyte is completely discussed. You can see in figure 6.16. Relationship of ionic conductance for transport number and equivalent conductance. The ionic conductance can be calculated from transport number measurement using the expression that may be derived as follows. You can see the derivation. Dependence of molar ionic conductance on viscosity of the solvent. Weldon's rule. It is obvious that greater is the viscosity of the solvent used to make the solution, less is the mobility of the ion, and hence ions is the ionic conductance. It is found that the product of the limiting ionic conductance of an ion and the coefficient of viscosity of the medium is constant, or the product of the equivalent conductance of an electrolyte at infinite dilution and the coefficient of viscosity of the medium is constant. This is called Weldon's rule. In case of ions, the above rule is found to hold good only if the ions are large in size. For smaller ions, if the solvent is other than water, even in the case, the results are not very satisfactory. The reason for the failure in case of smaller ions is that they are solvated to different extents and different solvents, and so their effective radii differ. Dependence of ionic conductance on temperature and pressure. Ionic conductance decreases with increase in pressure, which is again considered to be due to increase in viscosity with increase in pressure. Application of Coleridge's law of conductance measurements. Determination of equivalent conductance at infinite dilution for weak electrolytes. As already mentioned that the equivalent conductance of a weak electrolyte at infinite dilution cannot be determined experimentally. Firstly, because the conductance of such a solution is low, and secondly, because the dissociation of such an electrolyte is not complete even at very high dilutions. The equivalent conductance of such an electrolyte at infinite dilution can be calculated using Collerash's law in any one of following two ways. Here the complete derivation and numerical problems on calculation. Here are some problem practice questions. Degree of determination of degree of dissociation. According to Arrhenius' theory of electrolytic dissociation, the increase in the equivalent conductance with dilution is internally due to increase in the dissociation of the electrolyte, the equivalent conductance at infinite dilution being maximum because the dissociation is almost complete. Thus is the equivalent conductance of a solution at any concentration C and is the equivalent conductance at infinite dilution. However, the relationship is found to hold good only for weak electrolytes. The value for the weak electrolytes can be calculated using Collerash's law discussed already in the first application. You can see the some problem and numerical questions. Determination of dissociation constant Ka for acids. Consider the weak acid H. Suppose we start with its initial concentration equal to C mole liter inverse and alpha it is the degree of dissociation. Then we have proceeding as it Ostwald's dilution law. Thus, knowing the degree of dissociation alpha at the concentration C, the dissociation constant Ka of the acid can be determined. The value of alpha can be obtained from conductance measurements as explained in the applications. You can see the here some problem on calculation of dissociation constant. Here's some problem practice question. Determination of ionic product of water. Ionic product of water is defined as the product of the H positive ion concentration and OH negative ion concentration in gram ions or moles per liter. As water dissociates to a very small extent to give H positive ions and OH negative ions, water may be considered to be a very dilute solution of H positive ion and OH negative ions in water, so that we have. Determination of the solubility of sparingly soluble salts. Salts such as AgCl, BaSO4, PbSO4, etc., which are considered to be almost insoluble in water, do dissolve in water through to a very small extent. This is why these salts are called sparingly soluble salts. The solubility of such salts, which cannot be found easily by any other method, can be calculated by application of Collerash's law and conductance measurements as follows. Conductometric titrations. In addition to the various applications discussed above, one of the most important applications of conductance measurements in the determination of endpoints of different types of titrations. The basic principle of all these titrations is that when one solution from the burette is added to another solution taken into the titration flask or a beaker, some ions of the latter solutions are replaced by those of the former and hence the conductance changes. A few examples are illustrated below. Titration of a strong acid with a strong base. Suppose a solution of HCl is to be titrated against NaOH solution. For this purpose, the acid solution is taken in a beaker and the NaOH solution in the burette. The conductance of the acid solution is noted initially as well as after successive additions of small amounts of NaOH solution. You can see the figure 6.17 conductometric titration of strong acid with a strong base. Titration of a weak acid with a strong base. Suppose a weak acid like acetic acid is titrated against a strong base like NaOH. The conductance of the acid initially is very low because of low ionization of the acid. However, as NaOH solution is added more and more, 1C, the acid solution the salt produced is highly ionized and hence the conductance keeps on increasing. The line AB as shown in figure 6.18. You can see the figure 6.18 conductometric titration of weak acid with a strong base. Titration of a mixture of a weak and strong acids with a strong base. You can see in the figure 6.19 conductometric titration of a mixture of a weak and a strong acid against a strong base. Titration of a strong acid with a weak base. You can see the figure 6.20 conductometric titration of weak, strong and acidic base. Fifth, conductometric titration of AgNO3 solution against KCl solution. Thus, as HCl is added, the net result in the replacement of CH3COO ions by Cl ions, as both these ions have nearly the same conductance, the conductance of the solution remains nearly constant till the end point is reached. After the end point is crossed, the excess HCl added results in the increase of conductance. Thus, the shape of the plot is similar to that shown in figure 6.21. Volume of KCl added replaces the volume of HCl added. An important precaution in all the above titration is that the solution taken in the burette should be about 10 times stronger than that taken in the titration flux core beaker, so that volume change of the later solution is negligible on the addition of the former solution. Advantages of conductometric titrations. Conductometric titrations have a number of advantages over ordinary titrations involving the use of indicators. These titrations can be used for colored solution when ordinary indicators fail. These can be used for the titration for even very dilute solution. These can be used for the titration of mixture of weak and strong acids as the endpoint in the titrations in the intersection of two lines. No extra care. The drop-wise addition from the burette is needed near the endpoint. Dissociation constant and the ionic product of water. Here the derivation, you can see this. Here the pH convenient representation of H3O positive ion concentration, you can see this. pH scale. Theoretically, a solution may have any H3O positive ion concentration and hence may have any pH value. However, practically the solution having H3O positive ion or OH negative ion concentration more than. This is because such solutions are not easy to obtain, and moreover, as the concentration increases, the degree of dissociation of the acid or the base decreases enormously. Hence, the pH range is taken as 0 to 14 for most of the practical purposes. The acidity or the alkalinity of a solution may be represented on the pH scale. You can see this.